just a rearrangement of that formula. And that is just this formula where we've set this equal to 0, we've set the shaft work equal to 0, and we're assuming that all of the inlet streams have the same inlet temperature, which is just T0. So we put EB on there simply to help us out when we're solving the problem, that we don't confuse the conversion that we can get from the energy balance with one that we can get from a design equation. So if I was going to plot the conversion versus temperature, what would it look like? So if you look at this,
Was it linear? Linear-ish?
it's linear-ish. Why is it linear-ish and not just linear? So look at the equation. What's stopping it from being linear? Or what assumption can we make to allow us to say that it's completely linear?
Something at the bottom. But it doesn't-
Something with the denominator.
Yeah, it's like
Yeah. But what? No, this is at the reference temperature. This is the standard state enthalpy of the reaction. Nope. That's already built in.
At the reference temperature, it's much greater than the delta C2
Right. That this term,
Yeah.
that the heat capacity change between the temperature that you're operating at and the reference temperature, that this energy term is much smaller than the delta H of reaction. And that's usually a pretty good assumption. So if you make that a simplification, then you see that the numerator is dependent on temperature linearly. The denominator is not dependent on the temperature at all, because this is just the reference temperature, not the temperature of the reaction. Yeah,
How come you don't have a generation term?
steady state.
Oh, true. Oh yeah.
I mean, the generation shows up in the delta H of reaction. But there, I guess generation, yeah, that's here. There's no accumulation because you're at steady state. But the generation shows up in, if you're just dealing with the streams in and out, you'll see the generation. But yeah, coming back to this, we get a straight line. Where does it start on the x? What temperature does it start at? So if this is 0, what temperature do we start at? T0, yeah, the initial temperature. And then it's linear. Okay, so I've drawn that on the board. What else have I just now told you about the reaction? It's exothermic, right. As conversion increases, the temperature increases. That means that the reaction is giving off heat. It's adiabatic, so where does that heat go? Well, it just stays in the system. And that increases the temperature. So this is for exothermic. And of course, I could draw this. I could draw it again for an endothermic, where it would look just like that. I'm actually going to take that off because we're going to use that later. Yeah. So the shape of the curve, just which direction it's pointing, depends on whether it's an exothermic reaction or an endothermic reaction. So we talked about this a little bit last time, when we gave an example for ammonia synthesis, and we looked at what the temperature would be at different conversions, and the temperature got to be a really, really large number. And that can be that can be an issue for multiple reasons. But where does this stop? Where does this plot stop? What value of conversion will I stop at? All right, I heard a few people say 1. Is that always true? No, why not?
If it's at equilibrium, we'll go to equilibrium.
Right, so remember that if we say a reaction is irreversible, just means that the equilibrium conversion is approximately equal to 1. But all reactions are reversible. All reactions have an equilibrium. This is just a simplification that we can make in order to solve problems more readily. But no, where this stops is at the equilibrium conversion, right? That's where I have to stop. If I go any further, nothing happens. So there was a problem on the test. We're not going to review it today, but it asked the question, if I keep slowing down the rate at which I flow reactants into a reactor and the conversion doesn't change, what conversion am I at? Equilibrium. Right? That's the only way that that's true. Otherwise, making a reactor longer or slowing down the reagents will lead to a higher conversion. We only hit that final value at X equilibrium, which can be 1 if the problem statement said it was irreversible. Yeah.
Now, equilibrium is like a thermodynamic long time scale consideration. So is it possible that you could kinetically trap it past the equilibrium conversion? Like you do the reaction in some way that you actually get higher than that, but then it would slowly work its way back to equilibrium?
Not without dumping in some product. You know, if I just dumped in some product. So Adam's point is if I'm here and I'm going here, so here's my reactant and product, is there any way that I can accidentally have too much product in the system? You know, I'm doing the reaction and somehow I just accidentally end up with too much product, and now I have to work myself backwards. The thing that you're forgetting is that they go through this exact same transition state. So the kinetic limitation of forming the product is the same as the kinetic limitation of going backwards. They both have to go through that same transition state. So there's no pathway by which I can go reactant to product that isn't reversible. So that's, I think it's called microkinetic reversibility or something like that, microscopic reversibility.
Couldn't you add like reactants?
Yeah, well, that's what I said. If you pull out some reactants or you dump in some products, yeah, you'll end up on the wrong side of equilibrium, and then the reaction will actually start to occur in the reverse direction, where the net reaction rate is going backwards. That's why, again, on the test, and I don't want to belabor it because we're going to talk about this later, but if you make a Levensspiel plot, 1 over the rate versus conversion, and now I have an equilibrated reaction, there's an asymptote at equilibrium because at equilibrium rates are 0, and therefore 1 over the rate is infinity, and beyond the asymptote, the plot flips over because you're actually doing the reaction in the reverse direction. But anyways, that's an aside. Yeah?
What if you didn't allow like dynamic equilibrium because you either remove products after they're formed, or if you like to freeze quench or something like that?
So the second topic we're actually going to talk about today, so it's a good segue. But the first topic, if I'm removing products, that's only changing the concentration in its relationship to equilibrium.
You get a higher overall conversion.
Yes, of a particular species. So that's more about sort of how you're defining conversion. But really in that case, you're sort of changing the equation that XE corresponds to. But yeah, I mean, one way to get around equilibrium for a single species is to remove one of the species, to essentially have a membrane reactor, for example, and be removing a product as you're doing the reaction. But without a membrane reactor, it's going to stop. Yeah?
If you would like, say you're like a factory and you accidentally ran the thing at a higher temperature, so your equilibrium is farther up, then could you accidentally, like, from doing that, you think that you were making more conversion because the equilibrium is farther to the right? But
So if you don't know what temperature you're at, yeah, you might get a very weird, you might get a conversion that appears to be above equilibrium. But of course, the physical process hasn't violated thermodynamics. You just don't know, you don't have all the information. You think you're at one temperature, but you're actually at another.
if that ever happens, then your temperature, whatever reading it back to
Yeah. So I mean, we're going to talk about, when we get to multiple steady states, which, you know, somebody asked the question last time when we made a plot of these two things, can there be multiple intersections? That's multiple steady states. When we talk about that, a lot of that is safety oriented. To make sure that you don't jump from one of those steady states to a higher value based on your inlet conditions and stuff like that. So we're actually going to talk a lot about safety stuff within the next couple of weeks. But you bring up a more direct question. Is the equilibrium conversion constant with respect to temperature? No.
So yeah.
You think it is? All right, we have one no and one yes. Anybody else want to weigh in? 2 out of 110 people. All right. It is not. The equilibrium conversion changes with temperature. So that's where we're going to start today. And we're going to come back to this plot, but we're going to fill in another line, which is how does the equilibrium conversion change with temperature? And then we're going to talk about ways in which we can, quote unquote, beat equilibrium. So some of them have already been brought up today, but we'll talk about them in more detail. So for today, we're going to be sticking with adiabatic. Don't forget all of the stuff that you learned about heat transfer. It's going to still be important. But right now, we're not going to worry about it. All right, so now let's do this first. Our discussion got a little ahead of ourselves. We're not quite going to jump to equilibrium. Okay, irreversible liquid reaction.